Hello and welcome, ladies and gentlemen. We are looking at activity 4.2 here. We are in packet 4, lesson 2, module 1. I know it's a lot, but we're just going to go ahead and jump right into it. So number 1 says construct circle R and circle S, each with radius RS. It says label the 2 points of intersection as points T and V. So I already have a bunch of constructions here. It's because I did all of the constructions for the first, I think 6 or 7 questions. Right here. So the first thing that you do is you put your point of your compass here on S and you draw the circle that goes around like this. And then you put the point of your compass on R and you draw the circle that goes around like that. So that's number 1, right? Sweet, construction done. So now 2 says draw line segments to 4 triangle RST. So you can see I have triangle RST right there. So that part's good. It says explain why the triangle created is an equilateral triangle. So we'll do that. So if you remember, okay, in the last packet we constructed hexagons, and one of the ways that we constructed hexagons was by constructing equilateral triangles, and the way that we did that was by taking the radius and then creating a chord of a circle. So if we're looking at this left circle here, okay, so just focus in on this left one, right? We have the radius, which is RS, and then we duplicated the radius as a chord, and then we connected that chord back with the radius, and that was one way that we made an equilateral triangle in the last packet. So that's how you know that it's an equilateral triangle. And then it says, what does this tell you about the relationship between point T and the endpoints of RS? So point T, and I know, sorry, I put it on the inside of the triangle, I was poor. Point T and endpoints RS. Well, if this is an equilateral triangle, then I know that all of these sides of RS are equal to each other, right? So I know that T is equidistant, or as far away from R as it is from S, right? Because both of these distances, RT and ST, are equal. So we know equilateral because of exercises from last packet, right? And then point T is equidistant, and it is one word. I just spelled it there. It's just how I remember to spell it. It is one word. Point T is equidistant from points R and S. Perfect. Okay, so it says in the previous activity, the worked example states that if a point is on a perpendicular bisector of a line segment, then it is equidistant from the endpoints of a line segment. So it says consider the converse of the statement. So here's our if-then statement, starting there, ending there. Okay, here's our hypothesis, or the if part, and then here's our conclusion, or the then part. So the converse would be if a point is equidistant from the endpoints of a line segment, then it is on a perpendicular bisector of that line segment. Basically saying that so this says if you have a point that's on a perpendicular bisector, it's equidistant from 2 points, and then the converse is saying if a point is equidistant from 2 points, then it is on a perpendicular bisector. Cool. So it says construct a perpendicular bisector of RS. Label the point where the perpendicular bisector intersects the line segment as point Q, which I've already done right here. Okay, so that part A here, we can just check that off. We're good to go. B says determine whether the converse is true. If this conjecture is true, what can you say about points T and V? So I would say determine whether the converse is true. So our converse again, okay, is that if a point is equidistant from 2 other points on a line segment, then it is on the perpendicular bisector of that line segment. So I would say it's definitely true. And then what can you say about points T and V? So now I want to look at T and V. Well, I know that T is equidistant from R and S. And I know that V is also equidistant from R and S, because if I were to connect SV and RV, okay, I would also create an equilateral triangle for the same reason that this RST, triangle RST, is equilateral. So that means that T and V are both equidistant. And so we just said that if a point is equidistant from endpoints of a line segment, then it is on the perpendicular bisector. So we would say points T and V are on the perpendicular bisector of line RS. And it's actually a line segment if you want to be really proper there. Okay? So there you go. Those points are on perpendicular bisectors. So now on to this next part. Okay, so question 4 here says, consider triangle QST, justify each measurement. So, okay, so QST now, looking at just this triangle right here, the right side of our equilateral triangle, okay? So point A says, determine each angle measure, which I've done, if you saw those, okay, and we'll look back at those in a second. And actually, I'll look at them right now. So we said that point Q is on the perpendicular bisector of line RS, which means that this is going to be a 90-degree angle. We know that angle QST is going to be 60 degrees because that's part of our original equilateral triangle. And equilateral triangles have interior angles of all 60 degrees, right? This would be 60, this would be 60, the whole thing, and then this would be 60. And because this has been unchanged, it'll stay 60. And then up here, this perpendicular bisector happens to also be an angle bisector. Okay, and actually the way that you would do it is 90 plus 60 is 150. We know that the interior angles of a triangle add up to 180, and the difference between 180 and 150 is 30. So if you didn't know that this was also an angle bisector, you could do it that way. Okay, so there are the measurements. That's part A. Part B says, if QS is equal to X, determine the measures of TS and TQ. Okay, well, so this is going to be, here we go. So QS is equal to X. So I want to determine the length of TS and TQ. So I'll do TS first because I think it's easier, and then TQ we'll do a little Pythagorean theorem to figure out, okay? So I know that QS is equal to X. I also know that QS is equal to half of RS because this is a perpendicular bisector. So that means that RQ is also equal to X, okay? How does that help me? Well, it means that RS, one side of our equilateral triangle, is equal to 2X. And because all sides of an equilateral triangle are same, that means that TS, which is one side of our original equilateral triangle, will be equal to 2x. So QS is equal to x, TS is equal to 2x, and then now to find TQ, we have to do a little Pythagorean theorem. So remember Pythagorean theorem, a squared plus b squared equals c squared, and we can only do this in right triangles, which of course we have because that angle created at point Q as a vertex is a 90-degree angle. So we said one of our sides is equal to x, and so x squared plus, now remember, okay, if we were to, the side C is always the hypotenuse, which is the side, the diagonal side, right? Or the side that's away from the 90-degree angle, okay? So that means that I have a squared will be x squared plus, I don't know what b squared is, equal to 2x, which is the side length of TS, okay, squared. So now, without changing the left side, x squared plus b squared, that stays the same. 2x squared is the same as 2x times 2x, which is equal to 2 times x times 2 times x, which is equal to 2 times 2 times x, which is equal to 4 times x, which is equal to 4x squared. Okay, and if you don't need to do all that to see this multiplication, you don't have to. This is just a way to visually see it. And the reason you can switch these is because in multiplication we can do them in any order, so it doesn't have to be 2 times x times 2 times x. The same, we'd get the same answer if we do 2 times 2 times x times x. Okay. Anyway, so that is 4x squared. So now I want to solve for b, right? Because this is the side length that I don't know. So I'd subtract x squared, subtract x squared. Now I get b squared is equal to 3x squared, right? Because 4x squared minus 1x squared is 3x squared. Just like 4 minus 1 is 3. And then now, sorry, but coming over here to the left side, I'm just going to rewrite this. B squared is equal to 3x squared. I'm going to take the square root of both sides because I want to get just b on its own. So I get b is equal to square root of 3 times x. Because the square root of x squared is just x, and the square root of 3 is some ugly number, so we'll just leave it as square root of 3. And then the way that I would like you to rewrite this, just because it's a little easier to see, because what will happen oftentimes if you write it like this line, you'll end up putting the x underneath the square root sign again, but if you put it out in front like this, that's less likely to happen. So the side length for TQ is x times radical 3, square root of 3, however you want to say it. Okay, so, and then we can go ahead and label that over here. So we'd say x rad 3 for the side length. So QS was x, TS was 2x, and then this side was x times radical 3. Sweet. Okay, so now we're on to number 5. It says Damon drew line AR parallel to line segment ST and then drew line RS. He marked 2 pairs of congruent angles. So here are the angles he marked congruent. Also, we can tell by his little markings here. This singular angle marking and this singular angle marking mean that these two are the same. And then these 2 here in ART and then these 2 in RTS means that these 2 are also the same or congruent, okay? So number 5 just says that, so it shows you this little diagram. And then we go ahead and move on to the next page. And this is still number 5, but it says, what conjectures did Damon use to mark the congruent angle pairs? Okay, well, so we know that TS, so if I were to extend TS, we know that TS and AR are parallel to each other. AR parallel to ST, right? So we know that these 2 lines are parallel, and then we know that RT is a transversal that goes through that those parallel lines, and we also know that RS is also a transversal that goes through those parallel lines. So we want to look at which conjecture did he use to say that angle BRA and angle RST are equal, right? So maybe if I rotate my paper this way, it'll be easier to see. Here's my parallel lines. Remember what we were talking about earlier? If I were to label all of these angles, right? Something about corresponding angles. So his conjecture that he used would have been the same one that we started with. If 2, and then I'm going to use a lot of symbols here. So if 2 parallel lines are cut by a transversal, then corresponding angles are congruent, right? So if 2, this is the symbol for parallel, if 2 parallel lines are cut by transversal, then corresponding angles are congruent. Boom, okay? So that's one of them. That's one of his assumptions, or one of his conjectures that he used. Now let's look at another one. So now we're looking at the same parallel lines, but we're looking at angle ART and angle STR, right? So sorry, reading upside down can be a little difficult. So we're looking at these 2 angles. These look like interior angles to me, okay? So something about interior angles. And then they also alternate what side of the transversal they're on, which is why they're called alternate interior angles. Okay, so his second conjecture that he used, so here's one. His second conjecture he used would start off the same. If 2 parallel lines are cut by a transversal, okay, but then the then part, the conclusion will be different. Then alternate interior angles are congruent. Okay, so those are his 2 conjectures. Those are his 2 assumptions that he made, or that he used to make those angle markings. Okay, so now part B here says consider the central angles TRS, TRA, and ARB. So TRS, so this one, TRA, which is this one that's marked here, and then ARB, which is this one that's marked as well. Okay, it says consider those central angles and their intercepted arcs, ST, so from S to T, TA from T to A, and AB from A to B this way. Okay, it says what is the sum of measures of these central angles? What is the sum of the measures of the corresponding intercepted arcs? Well, okay, if we look at these angles, I know that this is going to be an equilateral triangle. The reason I know that is because you can see that the radius has been duplicated as a chord and then connected, which is the same reason we said it was an equilateral triangle earlier. So I know that this is going to be 60 degrees, okay? And then, well, actually, so there's a couple different ways you could do this. You could reason why all of these are equal to 60 degrees, or we could know that on a line, right, because on the line BS here, or on line BR, okay, on this line, this horizontal one, we know that the angle measure of one side of a line is always 180 degrees, right? So for line BS, okay, we know that this side of the line is going to add up to an angle measure of 180 degrees. So we know that these central angles, SRT, TRA, and ARB, are going to add up to 180 degrees. Okay, so some of the central angles, sum CA for central angles is 180 degrees, right? And then what is the sum of the measures of the corresponding intersected arcs? So sum intersected arcs, okay? Well, let's look at this. Okay, BS is also a diameter of our circle, and we know that because it's a chord. Remember, a chord is a line that has its line, or a line segment that has both endpoints on the circle. So B and S are both on our circle here, and they go through, and it goes through the center of the circle R. So a diameter is a special type of chord, so both of its endpoints are on the circle, but it also traverses or goes through the center of the circle, which BR or BS does. So because it's a diameter, we know that the two arcs that it creates in our circle are 180 degrees, right? Because it kind of cuts our circle right in half, and our circle has 360 degrees all the way around it, and then so cut that in half and we have 180. So it would also be 180 degrees. Okay, so C says, using Damon's diagram, what can you conjecture about the sum of the measures of the interior angles of a triangle? Explain your reasoning. So what can you conjecture about the sum of the measure of the interior angles of a triangle? Explain your reasoning. Okay, well, okay, and this is one that this is a conjecture we've already made, and the easiest way I think to look at it is to look at our equilateral triangles. Okay, and so our equilateral triangles have 60, 60, and 60 degree angles. So we would just say that all triangles have a sum of interior angles that is 180 degrees. Okay, and so I didn't do this as an if-then statement. If you look in the answer book, okay, they probably have this as an if-then statement somehow, but I'm going to go ahead and say that this is okay because this is a conjecture that we've already made and that we're already pretty confident about. We haven't proven it quite yet, but we are getting there, okay? So on to the next thing. This is the last page, so we got two more problems. Okay, so it says, a portion of Damon's diagram is shown. Consider triangle RST. So angle TRB, this angle right here, okay? TRB is an exterior angle, and RST, so RST, so this one, and STR, this one, STR, okay, are remote interior angles. So these are new vocab words. Okay, so if I just looked at the triangle RST, I'm drawing out here so we don't have to worry about the circle. So if I just have my triangle RST, these are interior angles. We've talked about that before. Okay, if I extend one line of my triangle, so I extend RS, okay, then this creates an exterior angle. Okay, if I were to extend this line, okay, if I were to extend RT, then this would be an exterior angle, right? So there's lots of exterior angles that we could create, right? And we could just keep extending lines and keep creating exterior angles. Okay, but it says, and then so that's exterior angles, and then remote interior angles. And so both these definitions are over here as well. An exterior angle of a polygon is an angle that forms a line, or forms a linear pair with an interior angle of the polygon. The remote interior angles of a triangle are the two angles that are not adjacent to the specified exterior angle. So, okay, I have TRB, that's my exterior angle. The interior angle that corresponds with that, that's the linear pair with this exterior angle, is TRS, right? These two make a linear pair. So remote interior angles are the two angles that aren't this angle, right? So 1 and 2, and that's why those are remote interior angles. Okay, so question 6 here says, what conjecture can you make about the measurements or the measures of the exterior angle TRB and the two remote interior angles RTS and TSR? Well, okay, RTS 60 degrees and TSR 60 degrees, right? And we know that because this is still an equilateral triangle for the same reason we talked about way back on the first part, or on the first page of this packet, right? So 60 and 60, and then we know that because this is this is a equilateral triangle, this is also 60. And so because TRB is a linear pair with the 60 degree angle, that means that this is going to be 120 degrees. Okay, so it says, what conjecture can you make about the measures of the exterior angle TRB and the two remote interior angles RTS and TSR? Right, so we can say, well, let's look. So this angle is 120, and these two angles are 60. So if I added these two angles together, it'd be 60 plus 60, which is 120. So what conjecture can we make we can say that, so we could say any exterior angle of a triangle will have the same measure as the two remote interior angles, okay, corresponding, and then this is, sorry, I got a little wordy here, to that exterior angle. Sometimes when I write it, when I'm writing, I don't think far enough ahead. So to say this in words, okay, to say this a little better, is that any exterior angle, the measure of any exterior angle is going to match up to the sum of the two remote interior angles that go with that one, right? Because if this is my exterior angle, the two remote interior angles that go with it are these two. But if I had my exterior angle was TS, and say this was like B over here, or we already used B, so say this was like, I don't know, Z. So if I had exterior angle TSZ, then the corresponding remote angles would be up here and over here, right? So basically, the two remote interior angles that correspond with the exterior angle are always going to be equal to each other in measure, right? Because 120 is equal to 120, okay? And so I got a little wordy there, I apologize, but that is what we were looking for there. So number 7 says each interior angle of a triangle has two corresponding exterior angles. Identify each exterior angle and use a protractor to test your conjecture from question 6. What do you notice? So I did these angle measures before, and I kind of cheated a little bit. So what I should actually have for my angle measures is some linear pairs, right? So 76 to get to 180, I would need to add 104 degrees. Okay, and then to get from 48 to 180, I would need to add 132. Yeah, 132 degrees. 132. And then to get from 56 to 180, I would need to add 124 degrees. Okay. So now I have all the angle measures of this entire thing. So it's asking you, what do you notice? Well, both the exterior angles that are created by one angle. So we'll talk about angle A here, with A being the vertex. We're looking at this top one. Both the exterior angles created by this are equal to each other, which makes sense because this interior angle isn't changing, and both of the exterior angles have to be linear pairs, so they have to add up to 180. So it makes sense that these two would add up to, or that they would be equal to each other, right? And then I did do this angle measure, and so this is kind of going to the vertical angles, so this is maybe a step ahead of what we're supposed to be talking about. We know that vertical angles, okay, and vertical angles meaning that they're opposite each other and at an intersection. We know that vertical angles are equal to each other in measure, which makes sense, again, because 76 equal to 76, and then 104 equals to 104. So another reason that these two are the same, right? And then 132, 132, 124, 124, right? All these vertical angles are equal to each other. So then, what do you notice? Okay, so this is just asking you what you notice. So what they're trying to get you to see is that all the exterior angles that are created off of the same interior angle match. So 104, 104, 132, 132, and 124, 124. Sorry about the little bit of a longer video. 4.2 is kind of a long activity. I hope you have a great day, and I will see you in class. Have a good one.